In Occluded Person Re-Identification, multi-person ambiguity, MPA, arises when multiple individuals are visible within the same bounding box, compromising system accuracy. Despite its significance, MPA has been overlooked in previous studies on occluded read methods. To address this challenge, we propose Keypoint Promptable ReIdentification, KPR, a novel formulation that utilizes semantic keypoints to indicate the intended target. Inspired by vision prompting, KPR complements the input bounding box with a set of semantic keypoints. However, existing read datasets lack the necessary pixel-level annotations for prompting. To bridge this gap, we introduce Occluded-PoseTrack ReID, a novel read dataset featuring strong interperson occlusions and keypoint labels. We also provide custom keypoint labels for 4 popular read benchmarks. Our KPR method systematically outperforms previous state-of-the-art approaches in various occluded scenarios, as demonstrated through person retrieval and pose tracking experiments. By addressing the critical challenge of MPA, our work contributes to the advancement of read research. The availability of our code, dataset, and annotations enables further study and underscores the importance of considering multi-person ambiguity in read tasks. Our proposed solution offers a promising approach to improve the accuracy of these systems. The Keypoint Promptable ReID, KPR, method addresses the challenge of multi-person ambiguity, MPA, in bounding box annotations, which can negatively impact identification models. By utilizing semantic keypoints as inputs, KPR disambiguates images with multiple individuals, leveraging either manual prompting by a human operator or automated prompting by an upstream pose estimation model. This approach draws inspiration from recent advances in promptable methods for vision transformers, such as SAM. The keypoint prompts guide the model's response, focusing on specific body parts and enhancing the accuracy of the identification process. In KPR, the keypoint prompts are designed to provide explicit guidance to the model, allowing it to concentrate on distinctive features that are crucial for identification. By doing so, the method mitigates the MPA issue, which arises when multiple individuals are present within a single bounding box annotation. This ambiguity can lead to incorrect associations between individuals, compromising the performance of identification models. The KPR approach offers a flexible framework, accommodating both manual and automated prompting. The manual approach involves a human operator providing explicit keypoint annotations, whereas the automated approach leverages an upstream pose estimation model to generate keypoint prompts. This flexibility enables the method to be adapted to various application scenarios, depending on the availability of human annotations or the accuracy of pose estimation models. By incorporating keypoint prompts, the KPR method achieves improved identification accuracy, demonstrating its effectiveness in mitigating the MPA challenge. Person re-identification, ReID, models face a significant challenge in dealing with multi-person ambiguity, MPA, where multiple individuals in a scene are partially occluded, leading to incorrect rankings. The proposed Keypoint Promptable ReIdentification, KPR, model addresses MPA by utilizing positive and negative keypoints prompts. KPR is a transformer-based model that takes an image and semantic keypoints as input, generating part-based features and their respective visibility scores. This allows the model to utilize only the visible parts for comparison, making it more effective in identifying occluded individuals. The model can process both positive and negative keypoints, which represent the target and non-target pedestrians, respectively. The key innovation of KPR lies in its ability to use prompts to identify the desired person in case of occlusion. Furthermore, KPR is designed to be prompt optional, offering flexibility to operate with or without prompts depending on the scenario. This is particularly useful in real-world applications where occlusions are common. To evaluate KPR, the authors introduce a new dataset called Occluded-PoseTrack ReID, OCCP-track, derived from the PoseTrack 21 dataset. This dataset provides high-quality keypoints annotations and features a substantial number of images with multi-person occlusions. The main contributions of this work are twofold. First, the proposal of KPR, a novel prompt-optional model for part-based ReID that explicitly addresses MPA, and second, the introduction of OCCP-track, the first multi-person occluded ReID dataset with explicit target identification through manual keypoints annotations. The author's method has achieved state-of-the-art performance on the occluded ReID task, surpassing previous approaches by 12.6% map and 9.2% rank 1 on the occluded Duke benchmark. This keypoint-centric paradigm shifts away from the traditional bounding box approach, providing a publicly available codebase, dataset, and annotations for evaluating promptable ReID methods. In the context of related work, the authors discuss multi-person ambiguity, a concept similar to non-target pedestrians, addressed in a previous study. However, their method explicitly disambiguates the intended ReID target during both training and testing phases, whereas the previous study focused on mitigating the negative impact during training. The authors contrast their novel keypoint promptable approach with traditional pose-guided methods, categorizing them into two groups: those inherently unable to address multi-person ambiguity and those with the potential to overcome it. They highlight the limitations of methods like BP Breed and PERT, which utilize pose labels only during training and cannot leverage additional information at test time to disambiguate multiple persons. In contrast, methods like ReID and PFD, which directly employ keypoints from a single person, have the potential to overcome multi-person ambiguity. However, ReID is restricted to utilizing spatial features at exact keypoints locations, overlooking critical appearance cues on entire body regions. PFD and other previous pose-guided methods incorporate pose information after appearance encoding has occurred, whereas the author's approach implements a prompt-aware appearance encoding, conditioning feature extraction on the input keypoints. This enables better feature disentanglement between the target and the occluders from the early feature extraction stages, resulting in more accurate representations. The authors also discuss recent works on prompting in vision, such as SAM, which employs a transformer encoder and a lightweight promptable decoder for interactive segmentation. In contrast, their approach directly prompts a feature encoder, allowing for more flexible and accurate feature extraction. Overall, the author's method provides a novel keypoint-centric approach to ReID, outperforming state-of-the-art methods and offering a more flexible and accurate solution to the multi-person ambiguity problem. The proposed Keypoint Promptable ReIdentification (KPR) model architecture leverages a SWIN transformer backbone, as illustrated in Figure 3. The input image undergoes tokenization using the conventional SWIN patch embed module, generating spatial tokens of dimension C. The image and optional positive, negative prompts are then tokenized and summed, converting raw image and keypoints information into C-dimensional tokens. Image tokenization produces HT times WT spatial tokens by embedding each 4x4 image patch through a linear layer. Keypoints tokenization utilizes two types of semantic keypoints as prompts: positive keypoints indicating the ReID target and negative keypoints indicating occluded or invisible body parts. The tokens are fed to the proposed multi-stage feature fusion (MSF) SWIN transformer, generating high-resolution feature maps. The feature map is then fed to a part-based head (PBH), which assigns a part to each token with a part classifier and averages all tokens of the same part to produce the final K part-based embeddings, F1, Fk, and their binary visibility scores, V1, Vk. A part I with no token assigned is considered invisible and ignored when computing two samples similarity. The KPR model is trained with two losses: a part prediction, PP, loss and a ReID loss. The entire pipeline is explicitly driven by the prompts, leveraging their semantic information to enhance body part localization and representation. Notably, the KPR model ingests multiple keypoints concurrently, unlike simple click, which prompts a transformer with a single 2D point and a previous mask for iterative segmentation. Batchwise interperson occlusion (BIPO) data augmentation is applied to generate artificial interperson occlusions, essential for the model to learn robust feature representations. The KPR model is illustrated for K equals 8, with a unique color for each body part: head, torso, right, left arm, right, left leg, and right, left feet. The tokenization process is crucial in converting raw image and keypoints information into a format that can be processed by the SWIN encoder. The authors introduce a keypoints tokenizer that categorizes prompt keypoints into K+1 groups, with the first group consisting of negative keypoints and the remaining K groups comprising subsets of positive keypoints corresponding to distinct semantic body regions. For each group, a unique heat map is generated by applying a Gaussian 2D kernel centered at each keypoint's location, with the kernel's standard deviation set to a fraction alpha g of the image width. The K+1 heat maps are then concatenated into a global spatial tensor of size h times w times K+1, which is linearly projected to produce prompt tokens of dimension c. The token fusion process involves summing tokens at the same spatial location, resulting in ht times wt spatial tokens with dimension c, which are then forwarded to the SWIN-based encoder. The design rationale behind this approach includes preserving semantic meaning before tokenization, differentiating positive and negative prompts, and distinguishing prompt information of different body parts for better part localization. Moreover, feeding the network with keypoint information before the encoding stage is crucial in enabling the network to disentangle the read target features from other person's features. This design also offers the flexibility to support segmentation mask prompts by replacing the heat map with a double-channel map of positive and negative segmentation masks. The authors utilize a SWIN transformer as the backbone feature extractor, which captures high-frequency details beneficial to read. They propose a multi-stage feature fusion strategy, denoted as MSF, to output feature maps with a high spatial resolution. Unlike standard SWIN, the MSF SWIN preserves the input token's resolution by bilinearly upsampling the outputs of all stages to the same resolution, concatenating them along the channel dimension, and passing them through a linear layer to obtain the final spatial token map. This approach enriches the granularity of the features and brings significant performance improvements. The part-based head module processes output tokens from the encoder, assigning each token to one of K body parts or the background through a tokenwise part classifier. This classification task is formulated with K+1 classes, producing part attention maps that showcase the probability distribution of each token belonging to a specific body part. Tokens assigned to the same body part are then averaged together, resulting in K part-based embeddings and their corresponding binary visibility scores. Invisible parts are given a visibility score of 0 and are ignored in further computations. The tokenwise part classifier is trained using human parsing labels derived from the human parsing dataset. The overall objective function for training the model consists of two components: the read loss supervised with identity labels, and the tokenwise part prediction loss, which is a cross-entropy loss applied on each spatial token. The read loss employed is the guild loss, combining an identity loss and a batch-herd triplet loss, with the distance function being the average of all local part-based distances. To address the issue of limited occlusion in most read datasets, the authors propose a novel batch-wise interperson occlusion data augmentation technique, BIPO. This method generates artificial interperson occlusions on training images, inspired by the copy-paste technique for segmentation. This augmentation aims to enhance the model's ability to handle occlusions during testing. The authors introduce a novel data augmentation technique called batch-wise interperson occlusion, BIPO, which generates artificial person occlusions that are consistent across image, prompt, and human parsing labels. This technique is crucial in enforcing the model to rely on the input prompts. BIPO works by randomly selecting a different person's image from the same training batch, contouring it with a segmentation mask derived from human parsing labels, and overlaying it on the main image. The human parsing label and keypoints prompt of the training image are then updated accordingly, and all positive keypoints from the occluder are added to the training prompt as additional negative points. The design motivation behind BIPO is to generate hard positive and negative samples for mining triplets, creating challenging scenarios for contrastive learning. This technique is illustrated in Figure 4a. During inference, the proposed keypoint re-identification (KPR) model processes each input image together with their respective keypoints prompts, producing K-part-based representations of the read target and their binary visibility scores. The global distance between a query image and a gallery image is computed as the average cosine distance of the part-based embeddings that are visible in both samples, as shown in equation 2. The KPR pipeline consists of two closely related architectural components. The first component is the prompt tokenizer, which encodes semantic keypoints information to disambiguate the read task. In the realm of person re-identification, read tasks, particularly in scenarios involving multi-person occlusions, the proposed Keypoint Promptable ReIdentification (KPR) model has been designed to leverage input prompts for enhanced performance. The KPR model comprises two primary components: the prompt-driven query encoder and the part-based head. The former extracts features from the input prompt, while the latter is responsible for localizing body parts of the target and constructing part-based features. The part-based head is explicitly supervised with human parsing labels during training to learn human topology. However, without specific loss incentivizing the model to leverage information from the input prompt, and with rare multi-person occlusions in most read training sets, the model does not rely heavily on the input prompts, leading to poor performance in multi-person occlusion scenarios. To address these issues, the proposed body-inclusive prompt occlusion (BIPO) data augmentation plays a critical role. By generating artificial multi-person occlusions during training, the model is compelled to rely more on the prompts as the sole reliable source of information to distinguish the true read target from the occluder. This results in a model that is proficient at leveraging prompt information and effectively handling multi-person occlusions. Furthermore, designing the part-based head without explicit reliance on the prompt renders the model prompt-optional, enhancing robustness against noisy or missing prompts while still enabling effective localization of the target's body parts. The model's performance is evaluated on four types of person retrieval setups, including non-occluded, object occlusions, multi-person occlusions, and both object and multi-person occlusions. Two standard person retrieval metrics are reported: the cumulative match characteristic, CMC, at rank 1 and the mean average precision, MAP. Additionally, the model is evaluated on multi-person pose tracking with the PoseTrack 21 dataset, reporting the HOTA performance metric, along with relevant submetrics such as association accuracy, ASA, detection accuracy, DETA, and the number of identity switches, IDs. The proposed Occluded-PoseTrack ReID dataset, built from the annotation available with PoseTrack 21, features keypoints and cross-video identity annotations. Unlike previous ReID datasets focused on street scenes, this dataset provides a new challenge for ReID models in handling multi-person occlusions. The OCCP-track dataset is introduced, comprising images from everyday life videos, primarily sports activities, with 1,000 identities and 17,898 images from 474 videos, and 1,411 identities with 13,412 images from 170 videos. To assess ReID model performance in multi-person occlusion scenarios, the most cluttered images of each identity in the test set are selected as query samples, and the remaining test images as gallery samples. Keypoint annotations are provided for standard ReID datasets using the PIF-PAF pose estimator, marking the intended target with an _target attribute and using other skeletons as negatives. The model implementation details include the use of ImageNet and solid or pre-trained SWIN backbones, setting the number of body parts to 8 for occluded Duke, OCCP track and 5 otherwise, and applying BIPO data augmentation with a 0.3 probability. The model is trained for 120 epochs with a batch size of 64 and a cosine annealing LR scheduler. A comparative analysis is presented, comparing KPR with and without prompts against leading occluded ReID methods. The results show that KPR emerges as the top performer overall. The performance of the method is also discussed on the OCCP track and occluded Duke datasets, which are suitable environments to assess the effectiveness of the promptable method due to the presence of multi-person occlusions. Person re-identification, a crucial task in computer vision, faces significant challenges in real-world scenarios, particularly when dealing with multi-person occlusions and pose ambiguities. To address these limitations, this research introduces Keypoint Promptable ReIdentification, KPR, a novel approach that leverages keypoint prompts to improve feature disentanglement and mitigate the negative impact of multi-person ambiguities. KPR is evaluated against several state-of-the-art (SOTA) methods on various datasets, including Market 1501, Occluded ReID, partial ReID, and the newly introduced Occluded-PoseTrack (OCCP-track). The results demonstrate KPR's superior performance, outperforming all previous occluded and pose-guided methods on the OCCP-track dataset, with a significant improvement of at least 6% in rank 1 and 6.2% in map. The key advantages of KPR lie in its ability to handle multi-person occlusions, process both positive and negative keypoints, and utilize a prompt-aware appearance encoding for better feature disentanglement. Furthermore, the flexibility of prompts being optional allows for greater adaptability in various scenarios. On the Occluded Duke dataset, KPR surpasses previous SOTA methods by at least plus 12.6% map and plus 9.2% rank 1, significantly narrowing the performance gap between holistic and occluded ReID. While the performance on Market 1501, occluded ReID, and partial ReID datasets has plateaued in recent years, KPR still performs on par with the state-of-the-art on Market 1501. This research introduces a promising approach to person re-identification, effectively addressing the challenges of multi-person occlusions and pose ambiguities, and opening up new avenues for future work. In this section, the authors present their novel Promptable ReID model's performance on various benchmarks and introduce a simple yet robust pose tracker, KPR track. They demonstrate that their proposed method achieves state-of-the-art performance in multi-person pose tracking in videos, outperforming other methods such as TRMOT, FairMo, Tractor++, and CoreTrack plus ReID. The keypoint prompts significantly enhance tracking performance by improving association accuracy and reducing identity switches, especially in multi-person occlusion scenarios. The authors also conduct ablation studies to analyze the performance impact of their architectural choices. These experiments reveal that using a prompt noticeably improves performance on occluded ReID and partial ReID datasets, which is consistent with earlier studies leveraging pose estimation to attain strong performance on these datasets. The table provided in the text illustrates the multi-person pose tracking performance in videos on PoseTrack 21, with KPR track showing superior results compared to its competitors. Additionally, the authors provide an analysis of the prompt optionality study, where they explore how different amounts of keypoints dropped affect the performance of the KPR track model with and without prompts. This study highlights the importance of keypoint prompts in enhancing tracking performance, particularly when dealing with occlusions and multiple targets intersecting paths. Overall, this section emphasizes the effectiveness of the author's Promptable ReID model and KPR track tracker in addressing challenges related to multi-person pose tracking in videos, especially in scenarios involving occlusions and complex interactions between individuals. The research paper presents a comprehensive ablation study on the proposed Keypoint Promptable Re-Identification (KPR) architecture, which aims to enhance person re-identification in occluded scenarios. The study explores various components of the KPR model, including the part-based head, multi-scale features, prompts, batch-wise interperson occlusion augmentation, and pre-trained weights from the Solider Foundation model. The ablation study, as demonstrated in Table 3, shows that each component plays a crucial role in improving overall re-identification performance. For instance, using a part-based head instead of a single global feature significantly enhances performance, as it allows for comparing only mutually visible body parts when dealing with occluded individuals. Increasing the feature map resolution also improves re-identification and overall performance, consistent with previous works. The use of positive and negative prompts helps disambiguate the intended re-identification target from other individuals, while the batch-wise interperson occlusion augmentation at training is essential for teaching the model to rely on the input prompt to identify the intended target among all candidates. The pre-trained weights from the Solider Foundation model enhance performance, although there is a domain gap between the street surveillance focus of Solider and the sports images from handheld cameras in the OCCP track dataset. Furthermore, the paper analyzes the test time robustness of KPR against noisy or missing prompts on the OCCP track dataset. By gradually removing a higher percentage of keypoints from the input prompt, the performance of the promptable KPR model, red curve, is compared to the non-promptable version, blue constant line. This analysis highlights the importance of the prompt in enhancing re-identification performance, particularly in scenarios where partial information is available. In conclusion, the ablation study and test time robustness analysis demonstrate the effectiveness of the KPR architecture in enhancing person re-identification in occluded scenarios. The paper emphasizes the significance of each component in achieving improved performance and highlights the potential for future research to further refine the model. KPR, a novel promptable ReID model, addresses occluded scenarios and multi-person ambiguities in bounding box-based inputs. This model offers practical flexibility by being prompt-optional, achieving state-of-the-art performance without prompts and outperforming the baseline with prompts. Evaluated on 3 popular ReID benchmarks and the novel OCCP-track dataset, KPR demonstrates its potential for pose tracking in videos. The model's performance is showcased through various figures, including Figure 6, which illustrates the impact of keypoint prompting on part attention maps, person retrieval, and pose tracking. KPR effectively leverages input prompts to localize the intended target, making it robust to occlusions and multi-person ambiguities. The model's performance with respect to the amount of multi-person occlusion is discussed in supplementary materials. KPR significantly outperforms the non-promptable baseline, even when a full prompt is provided, and remains competitive with few or no keypoints, highlighting its prompt-optional capability. This research introduces KPR as a practical and flexible solution for ReID tasks, offering a new paradigm for promptable ReID. The codebase, keypoint labels, and the proposed OCCP-track dataset will be released to encourage further research on this new promptable ReID paradigm. Funding for this work was provided by Sportradar, the Walloon Region Project Reconnaissance, and the FNRS. This page presents a comprehensive list of research papers, articles, and studies that have significantly contributed to the understanding of quantum computing and its potential applications. The list is organized chronologically, providing an overview of the evolution of quantum computing research over time. The earliest entries date back to the 1980s, when quantum computing was still in its infancy. These pioneering works laid the foundation for future research, exploring theoretical models and initial experiments on quantum bits, qubits, and quantum algorithms. As the field progressed, so did the complexity and depth of the research. Papers from the 1990s and early 2000s delve into quantum error correction, quantum cryptography, and the development of quantum algorithms such as Shor's algorithm and Grover's algorithm. These studies demonstrated the potential power of quantum computing in solving complex problems more efficiently than classical computers. In the mid-2000s, the focus shifted towards experimental implementations of quantum computing, with researchers exploring various quantum hardware platforms like superconducting qubits, ion traps, and photonic systems. This period also saw significant advancements in quantum simulation techniques, which allowed scientists to model quantum phenomena on classical computers. The latter half of the list covers recent developments in quantum computing, including the advent of quantum annealing, variational quantum algorithms, and the rise of quantum software technology. Notably, this section highlights the increasing involvement of industry partners, such as IBM, Google, and Microsoft, in quantum computing research. The list concludes with ongoing and future directions in quantum computing, emphasizing the need for continued advancements in quantum error correction, scaling up quantum systems, and developing practical applications for quantum computing. In the realm of sports analytics, computer vision techniques play a pivotal role, particularly in soccer. The SoccerNet 2022 challenges aim to establish benchmarks for various tasks, including action spotting, replay grounding, and player identification. One promising approach is the Trans-ReID model, a transformer-based object identification method that has demonstrated impressive results in identifying players across multiple frames. The triplet loss function, a crucial component for person identification, is also discussed, despite its limitations. The Deep Sport TradeArv2 dataset, a comprehensive multi-sport dataset, is essential for developing and evaluating algorithms in sports analytics. This dataset is complemented by the Microsoft COCO dataset, a widely used benchmark for object detection and segmentation tasks. The simple-click interactive image segmentation method, which leverages simple vision transformers for efficient segmentation, is also highlighted. Additionally, the paper touches upon the Mode Challenge 2015, a benchmark for multi-target tracking, and the TrackLab library, a tool for tracking and re-identification in sports videos. By providing an in-depth analysis of current advancements in sports analytics, the paper underscores the importance of robust datasets and efficient algorithms for accurate player tracking and re-identification. The authors present a comprehensive analysis of 15 variables influencing the efficacy of a novel machine learning algorithm in predicting patient outcomes. These variables encompass a range of factors, including demographic characteristics, clinical indicators, and treatment modalities. A key component of the analysis involves the application of a Bayesian neural network to model the complex relationships between these variables and patient outcomes. The authors employ a Markov chain Monte Carlo (MCMC) algorithm to estimate the posterior distributions of the model parameters, allowing for the quantification of uncertainty in the predictions. The results of the analysis indicate that the inclusion of certain demographic and clinical variables significantly enhances the predictive accuracy of the algorithm. Specifically, the incorporation of age, comorbidity status, and medication adherence data is shown to improve the model's ability to forecast patient outcomes. The authors also investigate the impact of different treatment modalities on patient outcomes, with a focus on the efficacy of combination therapies. The results of this analysis suggest that the use of multimodal treatments is associated with improved patient outcomes, particularly in cases where individual treatment modalities are insufficient. A key finding of the study is the identification of a nonlinear relationship between certain clinical indicators and patient outcomes. This nonlinearity is captured through the use of a generalized additive model, which allows for the incorporation of complex interactions between variables. The study's results have important implications for the development of personalized treatment strategies and the optimization of patient care. Limitations of the study include the reliance on observational data and the need for further validation of the findings in prospective studies. Future work will focus on integrating the algorithm with electronic health records and exploring its application in real-world clinical settings. This section of the research paper presents a comprehensive review of various state-of-the-art methodologies and techniques used in the field of occluded person re-identification. It emphasizes the importance of addressing the challenges posed by partial visibility, such as pose estimation, feature disentangling, and domain adaptation. The authors discuss several key contributions from recent studies, including the use of transformer-based architectures for learning to know where to see, Yang et al. 2021, focusing on visible regions with semantic guided alignment models, Yang et al. 2020, and utilizing multi-head self-attention networks for robust re-identification, Tan et al. 2023. They also emphasize the role of high-quality datasets, like Deep Sport Tradarv 1, Van Zandijk et al. 2022, which provide essential annotations for training and evaluating models. Moreover, the paper delves into the concept of person transfer GANs to bridge domain gaps in re-identification tasks, Wei et al. 2018, and the significance of learning to understand the visibility of different body parts, Wang et al. 2020. Furthermore, it touches upon the importance of real-time multi-object tracking, Wang et al. 2020, and the development of single-scale global representations for re-identification, Yan et al. 2021. In addition, the authors summarize the findings from a survey on deep learning for person re-identification, Yi et al. 2022, emphasizing the need for further research in this area to overcome existing limitations and challenges. Overall, this section provides a thorough overview of the current advancements in occluded person re-identification, highlighting the complexities involved and potential avenues for future work. In person re-identification, a crucial task in computer vision, learning to disentangle scenes is essential for improving accuracy. As proposed by Zhang et al. 2021, disentangling the person from the background scene allows for more precise individual identification. Building on this concept, patchwise high-frequency augmentation has been introduced for transformer-based person re-identification by Zhang et al. 2023. This approach enhances image quality used in the re-identification process, leading to increased precision in models. The technique involves augmenting image patches with high-frequency information, which enables transformers to capture subtle details and reduce the impact of background noise. Furthermore, the paper explores the concept of part-aware feature alignment, which aims to align features from different body parts across various cameras and views. This approach facilitates more accurate person re-identification by leveraging the spatial and temporal relationships between body parts. The research also investigates the effectiveness of multi-scale feature fusion, which combines features from different scales to capture both local and global information. This fusion enables person re-identification models to capture a more comprehensive representation of individuals. The paper's methodology is evaluated on several benchmark datasets, including Market 1501, Duke MTM Creed, and CUHK03. Experimental results demonstrate the superiority of the proposed approach in comparison to state-of-the-art methods, highlighting its potential for real-world applications. In the supplementary materials section, the authors delve into additional details regarding their novel Occluded-PoseTrack ReID dataset and the KPR-track pose tracking method. They provide supplementary qualitative and quantitative results to offer a more comprehensive perspective on their research. The code, annotations, and proposed dataset are available at link. The authors present a study on the robustness to multi-person occlusions, comparing the performance of KPR with its non-promptable version under various occlusion levels on OCCP-track. To quantify the multi-person occlusion level, MPOL, of a query sample I in the query set Q, they compute the difference between the number of negative keypoints Ni and the number of positive keypoints Pi. Then normalize this value over the set Q to obtain a percentage as follows. MPOLI equals Ni minus Pi minus min j element of Q, Nj minus Pj, max j element of Q, Nj minus Pj, minus min j element of Q, Nj minus Pj. 3. The plots in Figure 7 demonstrate that the utilization of prompts leads to at least a 10% performance enhancement in scenarios with heavy multi-person occlusions. This indicates the efficacy of keypoints prompts in disambiguating the intended read target among multiple pedestrians. Moreover, keypoint prompts contribute to better part-based feature extraction, which explains the performance boost in scenarios with low occlusion scores. The Occluded-PoseTrack ReID dataset, or simply OCCP-track, is a new ReID dataset built out of the annotation available with PoseTrack 21. PoseTrack 21 is a popular video benchmark for multi-person pose tracking, featuring keypoints and cross-video identity annotations. The authors provide a train-test split of Occluded-PoseTrack ReID based on the original train-validation split of PoseTrack 21. Important numbers about each split are summarized in Table 4. Similar to the original dataset, the train and test splits do not have overlapping video scenes and therefore do not share identities. The performance of the Keypoint Promptable ReIdentification (KPR) method is evaluated with respect to multi-person occlusion levels of queries, as illustrated in Figure 7. The OCCP-track dataset is utilized, comprising 1,000 randomly sampled identities from the PoseTrack 21 train set and all 1411 identities from the test set. Each tracklet is uniformly sampled, ensuring a minimum of 4 and a maximum of 20 image crops per identity. The test set is divided into a gallery set and a query set, with 20% of each identity's images added to the query set and the remaining 80% to the gallery set. The 20% most occluded samples from each identity are chosen as query samples, with occlusion scores computed using equation 3. This sampling strategy makes the dataset more relevant for evaluating methods that address occlusions and multi-person ambiguity. Unlike previous datasets, each query sample is compared against all galleries, regardless of whether they are from a different video or not. PoseTrack ReID contains identity labels valid across the entire dataset, as a given identity can be spotted in multiple videos. The characteristics of each PoseTrack ReID subset are presented in Table 4, including the number of identities, images, and videos in the train, query, and gallery sets. The scale of the dataset is compared to existing popular ReID benchmarks in Table 5. Notably, the authors discourage the use of re-ranking to evaluate ReID methods on this dataset, ensuring a more accurate assessment of method performance. The authors present a comprehensive comparison of their proposed Occluded-PoseTrack ReID dataset with other popular ReID datasets in Table 5. This table highlights the unique characteristics of each dataset, including the number of identities, cameras, images, release year, and whether occlusions are present. The authors then discuss the annotation requirements for their method, which involves two types of annotations: keypoint labels for prompting at both train and test time, and human parsing labels only used at training time by the part prediction loss. For existing datasets, such as Market 1501, Occluded ReID, Partial ReID, and Occluded-Duke, keypoint labels are generated using the PIV-path pose estimation model, while human parsing labels are obtained from BP-breed. For Occluded-Duke, manual correction of approximately 10% of the query samples is performed to ensure accuracy. In contrast, for the proposed OCCP-track dataset, keypoint labels are directly obtained from the original PoseTrack 21 dataset, while human parsing labels are generated using segment anything, prompted with the target's person keypoints, to produce a consistent segmentation mask. The authors experimented with employing SAM to directly generate human parsing labels but found it to be inaccurate. Instead, they combined SAM and PIV-path to achieve the most accurate human parsing labels. The authors then provide further details on their proposed pose tracking method, KPR-track, which leverages two components from ByteTrack: the tracklet lifetime and the detection-based tracking approach. The authors of the research paper employ a Keypoint Promptable ReIdentification method in their multi-object tracker, utilizing a cycle management mechanism and a multi-stage association strategy based on the confidence level of detections in the current frame. This is achieved by fine-tuning the YOLOX object detector and the hour-net pose estimator on the PoseTrack 21 trainset. Notably, the proposed tracker does not utilize spatiotemporal information, unlike most existing state-of-the-art multi-object trackers. However, it can be easily extended with additional spatiotemporal cues, such as a Kalman filter with bounding box IOU, to further improve performance. The Keypoint Promptable ReIdentification (KPR) method is used to provide appearance cues to the tracking pipeline, which is trained on the OCCP track trainset. Since KPR outputs part-based features, the authors adjust ByteTrack's tracklet management strategy to compute a tracklet's part-based features as a moving average of the part-based features of the underlying detections. If some body parts are not visible within a detection matched to a given tracklet, the corresponding part-based features in the tracklet are not updated. Performance is reported on the PoseTrack 21 validation set, with additional comprehensive state-of-the-art comparisons and ablation studies provided in Tables 6 and 7. The ablation study includes experiments demonstrating the impact of KPR components when starting from the solid or pre-trained weights, as well as an experiment showcasing the impact of keypoint prompting on a global ReID method. Qualitative results are provided in Figure 8. Implementation details include fine-tuning the solid or backbone, where the semantic_weight parameter has minimal impact and is set to 0.2, and the keypoint tokenizer is frozen for the first 20 epochs. Label smoothing regularization rate epsilon is set to 0.1, and the triplet loss margin alpha is set to 0.3. Token input and output dimensions C and CO are set to 128 and 1024, respectively. Part-based embeddings are downsampled to an output dimension of 256 using a simple linear layer followed by batch normalization and ReLU operation to reduce memory footprint. This section of the research paper presents a comprehensive comparison between the proposed KPR method and several state-of-the-art (SOTA) methods in person ReIdentification tasks. The comparison is conducted across multiple datasets, including Market 1501, Occluded ReID, Partial ReID, Occluded-PoseTrack, and Duke. The results are presented in Table 6, where KPR's performance is evaluated with and without prompts for both the in and sol variants. In general, KPR outperforms or matches the performance of SOTA methods in most datasets, demonstrating its effectiveness in handling object and person occlusions. The paper also details the experimental setup used for training KPR, including data augmentation techniques such as random cropping, padding, and erasing, as well as the use of a cosine annealing learning rate scheduler. The model is trained on an NVIDIA RTX 8000 GPU with a batch size of 64 samples from 16 identities. Overall, this section provides a thorough evaluation of the KPR method against existing SOTA methods, showcasing its robustness and efficiency in person identification tasks, particularly when dealing with occlusions. This table presents a comprehensive ablation study of the proposed KPR architecture, which includes various components such as part-based head, PBH, multi-scale features, MSF, prompts, batch-wise interperson occlusion, BIPO, and pre-trained weights from Solidar, SOL. The table evaluates the performance of different combinations of these components on the Occluded-PoseTrack and Occluded-Duke datasets. The results indicate that incorporating all components, row 8, yields the highest performance, with a significant improvement in MAP and R1 scores. Disabling the prompt, row 1, results in a decrease in performance, while enabling it, row 5, improves the performance. Adding PBH, row 2, also leads to a decrease in performance, but combining it with MSF, row 3, increases the performance. Including BIPO, row 4, further enhances the performance, and adding SOL, row 8, leads to the best performance. The study also explores the effect of disabling individual components while keeping others enabled. For instance, disabling PBH, row 10, or MSF, row 12, reduces the performance, while disabling both, row 11, leads to a more substantial decrease. Disabling prompts, row 6, or BIPO, row 7, also negatively impacts the performance, although the impact is less significant than disabling PBH or MSF. The study demonstrates the importance of each component in the KPR architecture, particularly the positive impact of incorporating all components. It highlights the significance of part-based head, multi-scale features, prompts, batch-wise interperson occlusion, and pre-trained weights from Solidar in enhancing the identification performance on occluded datasets.